Hello everyone. So today let's solve the problem interesting graph and apples, right? So this was asked in the code forces beta round 9 for the division 2, right? So you can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So let's see what the question states here, man. Yeah. Now, yeah, we have been given n vertices and m existing undirected edges, right? We have been given n vertices and m existing undirected edges. I mean, loops and multi edges are allowed here, right? So we have to add the minimum number of edges. What we need to do here, add the minimum number of edges actually, right? Add the minimum number of edges. So every vertex belongs to exactly one simple cycle, right? So we have to add uh, minimum number of edges here so that every vertex belongs to exactly one simple cycle. Every this one vertex belong to one simple cycle, right? One cycle. Let me write it over here. So if it is impossible, then we have to print no. If it is possible, then if it is impossible, then we have to print no. If it is possible, then we have to print yes. The number of also the number of added edges and the exact edges, right? So if it is possible, then we have to print s along with the this one. What do we call number of added edges, right? So number of added edges. This one number of added edges. I'll just write here added. Sorry, just remove this one. Yeah, number of added edges here. Yeah, I'll just write biggie here. Number of added edges along with the this one, the exact edges, right? The exact edges as well. We have to output these things actually, right? So if it is impossible, then we have to print no. If it is possible, we have to print yes. Then along with that, we have to print the number of added edges and the exact edges, right? So we have to print the lexicographically smallest sequence to add, basically, in simple terms, right? Now we have um, we have to preserve the existing edges and allow the adding loops or multi edges as well. Yeah, keep this in mind. We have to preserve existing edges. This is fine. And also we have to allow adding loops or multi edges. So this is also very important, right? Just I'll read this one again. We have to preserve existing edges and allow adding loops or the multi edges. So we have to choose the minimal and lexicographically smallest additions. What we need to choose? We have to choose the minimal and lexicographically smallest additions, right? So this is fine. So let me read the question out loud. Just listen to this carefully, man. Yeah. So I'll just go from. So we have been given n vertices and m existing undirected edges. Nothing but loops and multi edges are allowed here. We have to add the minimum number of edges. We have to add the minimum number of edges. So every vertex belongs to exactly one simple cycle. Exactly one simple cycle, right? A cycle visiting its vertex once, right? Nothing but the loops count here. If it is impossible, then print no. Otherwise, we have to print yes, the number of added edges and the exact edges, right? Exact edges to add here. So this is fine, I believe. Yeah. So these three things we have to output here, right? So next we have to preserve the existing edges and allow adding loops or the multi edges. We have to choose the minimal and lexicographically smallest addition, right? Yeah, this is simple one, man. Yeah, let me delete this one. Yep, let me come to the input output part, right? So this is the number of edges. So let me write it over here. So this is nothing but the number of edges n, number of nodes, sorry, n, and this is nothing but the number of edges, right? So I can just write it over e or something, m, let me write it over here, right? So this is nothing but the number of edges. See here, number of edges we have here is 2, 1, 2, and 2, 3. This is nothing but the number of nodes. See here, 1, 2, 3, 3 nodes we have, right? So this one we can just represent in this way, right? So 1 to 2 we have and 2 to 3 we have. So total number of nodes we have here is 1, 2, 3. So that's what they have given here. And m is nothing but the number of this one. What do we call edges? So we have this one. 1 to 2, so this is undirected graph. This is one edge and this is one edge, right? 1 to 2 and 2 to 3. So the output that we need to get here is yes along with 1 and 1 3. Yes, because it is possible, and the number of added edges here is 1, and the exact edges to add is here this one 1 3, right? So this is fine. Yeah, now let me delete this one. Yeah, as we have this one, what do we call, as we are familiar with the question, let's do one thing. Let's quickly discuss the approach followed by the complexities, and then let's write the code. First, as usual, let's discuss the approach part. So here I have considered the same first example that they have given in the question, right? So this is n, this is m. So these are the edges, basically output that we need to get here is s followed by 1 and 1 and 1 3. Right. So this one, we will be making use of the DSU one. DSU nothing but the disjoint set union to solve this particular problem. Right. So let's move on with the further things. Let's move on with a step-by-step explanation here. So n is 3, m is 2, edges here 1, 2, and 2, 3. The first thing here would be we'll keep the degree count. We'll keep the degree count a of b here for the each vertex and the DSU as well. As I've said, we'll be going with the DSU, right? We'll keep the degree count in the sense degree, right? You know, in degree and out degree. So we'll keep the degree count a of b for each vertex and the DSU, nothing but this one, f represented by f here, to track the components. Fine. Now, let's move on with the second, this one point. If any vertex degree is greater than 2, suppose if any vertex is having the degree greater than 2, then it is impossible, then it is impossible, right? Just keep this in mind, right? We have been given m equals to 2 here, right? If any vertex degree greater than 2, it is impossible. If adding edges would create greater than one cycle in any component, then also it's impossible, right? So if adding edges, suppose if we have accordingly with the question, we have to add the edges, right? We have to display that one in the output as well. If adding edges would create greater than one cycle, then in any component early in input, then also it is impossible. Two cases we have written where it is impossible, right? So just keep this in mind. Otherwise, we have to repeatedly connect the vertices with degree less than 2, less than 2, preferring the smallest possible lexicographical pairs, right? I comma j, this one, while avoiding joining two vertices already in the same component, unless allowed by final conditions, So this yields minimal added edges k equals n minus m. So this with this point will be going basically kind of formula. So basically, while avoiding joining two vertices already in the same component unless allowed by the final conditions, right? So this will yield to the minimum added edges that is equivalent to this. Remember this one, this is important. This will be using basically. This yields to the minimal added edges k equals n minus m. This is fine. So for the example that we considered, for the first example, degrees are 1 to 1. Degrees are 1 to 1, right? So we have this one, what do we call, the edges 1 to 2 and 2 to 3, right? So we have degrees are 1 to 1 basically, right? So this is fine, we know. And we need one more edge, actually we need one more edge. So, and one more thing, they have mentioned in the question, it consists of this one, graph may be either directed as well as the undirected, right? So, degrees for this are 1 to 1. This is fine. We need one more edge. We need one more edge. Smallest valid pair to close cycles is, so this one, 1 comma 3, 1 comma 3. You can just check the graph that I had drawn earlier, right? So you can just check that one, right? So this one, smallest valid pair to close the cycles is 1 comma 3. So what we will do, we will draw this one as, we'll display this one as the output. Only one edge, right? Along with the one edge. So only one edge, 1 comma 3 and 1 3. So this we will be outputting as the this one reset. This we have to output. Yes, it is possible. And one edge we have added, and smallest valid pair to close cycles is 1 comma 3. That edge we will be adding this one as this one. Yeah, we will be outputting this one. Yeah, this is fine now. Yeah, this is the output that we got, S1 and 1 3, which is equivalent to the output that they have given for the out example 1 within the question, this one, S1 and 1 3. So our approach works absolutely correct here. Our approach works absolutely correct. As we are completely familiar with the approach, let's do one thing. Let's quickly move on with the complexities part, right? So what are the time complexities here? The time complexity is big of n square plus m. So why it is big of n square plus m here? Uh, Basically, yeah. So here primarily, let me tell you one thing here. Reading m edges costs this one because of m along with the a of n. A of n is nothing but the this one. What do we call? Inverse Ackermann, right? So that's the small value we can just consider here because of n square m overall. Reading m edges costs because of m for the DSU plus the greedy double loop that in the worst case, right? Scan space I comma j up to big of n square. So overall time complexity we can just write it big of n square plus m. And what would be the space complexity here? The space complexity would lead to big of n, right? So arrays f and a of size proportional to the n here. Here fixed basically. In the code it is 505 fixed basically. Just remember this one. Yeah. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n square plus m and big of n respectively. Now, as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. So let's start writing the code. We'll be making use of the this one fast input output. So I'll just go with java.io input output package along with the different utilities as well. So I'll import java.util.star. This is fine. Next, let's go with a class here, right? So this is fine. So within the main class, what we'll be doing first, we'll be going with the DSU parent array. Along with that, we'll be going with the degree counters for each vertex, right? So I'll just go with here static in f here equals new end of a fixed array of 505. I said it on the while discussing the complexities, right? So we'll be going with the same accordingly with the constraints actually. So this is fine. A equals, so let me go with new int of 505. Yeah. Now let's do one thing. Let's find with the path compression. So as we are making use of the DSU, as I've said, we'll be making use of the DSU, right, to solve the problem. So we will be going with a this one find actually. What we will do within the find method, if you know the algo, so we will be going with the path compression along with for the this one finding the representative or parent of the x, right? So basically we'll be returning the representative of x. So let's do that very quickly, man. So here let me go with static in find. This is simple. Let me consider the parameter x. This is fine. So let me return here. What should we return? F of x. This is equal. If it is equal to x, then what we need to display? We need to go with a this one. Sorry, x actually. If not, then we have to go with f of x that is equal to find of, we have to recurse, right? So this one is find of f of x basically. So this is fine. Yeah. Now we are done with this part one. Let me come out of this one entirely. Now after that, let's go with let's move on with the main method. So let me go with main here. Let me remove this and let me give here throws input output exception. Yeah. Now let me paste this one. So what I have pasted only, this is related to this is completely related to the input output part. Fast input, buffered radar, fast output, print writer we have made use of, right? So and the string tokenizer we have to read this line. First one, number of nodes as well as the edges, right? So this one we have made use of the string tokenizer here. N and M are nothing but this one. N and M same thing. 3 and 2. So this is fine. So next, let's move on with the further things here, right? So this is fine. So if there are already more edges than vertices, then it is impossible to form exactly one cycle, right? So that one we have to write. We have discussed this one already, right? So this one will be if m greater than n, then let me go with out dot println. So this is fine. Let me display no here. This is possible. Yeah. Now I'll just give here. Sorry. 1 second. Yeah. Let me give here out dot flush. This is fine. Out dot flush. This is fine. Let me give return as well, man. Yeah. This is Yep. Let me come out of this one entirely. Now, let's initialize the DSU parents, meaning, so each vertex is its own parent initially, right? So let me go with a for loop here. This one in I equals 1, I less than or equal to n, I plus plus, this is fine. F of I is equivalent to the I. Yep. Now let's do one thing. Let's read the m existing edges. How can we do that? So let's move on with the iteration again. So this one, I equals 1, I less than or equal to m, I plus plus. So within the for loop, what we have to do here, let's go with the string tokenizer. So I'll just copy this one. Let me copy this and let me paste it over here. This is fine. Yeah. Now let me go with x equals x and y we have to go with, right? So the same thing, I'll just copy here. This is fine. Let me paste it over here. Instead of n, I'll just give x here. Instead of m, let me give y here. Right. So this is fine, man. Yeah. Now, let's move on with the further things. We have to increase the degree counters for both endpoints, right? So this one will be a of x increase. Let's increment this one. Also, let's go with a of y plus plus. We have to increase degree counters for both endpoints. We have successfully done that one, right? So this is fine. Now, let's move on with the further points. So if x and y already in the same DSU component, and if we are adding an edge before processing, this would create a second cycle inside the current component. It is not allowed accordingly with the question, right? Criteria within the question. So original code, let's go with I less than or equal to n1. Yeah, this is part of the given solution logic as well, right? Let's do one thing. Let's write it in this way. See, just look into this one. If we are going with a find of x, this is fine. If it is equivalent to the find of y, we have already written the helper method find, right? As we are going with this one, so this one has to be written within the parenthesis, this x as well. So why have I written the array? Actually, find of x equals find of y, and I not equal to n basically. Then what we need to do? Let me go with. So let me scroll this one. Just give me a second here. Out dot println. So what we need to print here? No, right? It is impossible. It is not allowed accordingly with the criteria of the criteria within the question, right? They have mentioned. So this one will be out dot flush, out dot flush. So this is also fine. Finally, let me return. Let me return. Return means we have to exit from there. So let me give return here. This is fine. So let me come out of this one entirely, man. Now let's go with a union. We have to union the two components by linking parent of x to the parent of y. So this is simple. I'll just go with find of x here. So we have to link this one, a parent of x to the parent of y, right? So this one equals find of y basically. Yeah. So this is simple, man. Let me come out of this one entirely now. Let me come out of this one entirely. Yeah. So now let's move on with the further things. We have many things to do yet. So where we have stopped actually. Yeah. We went with the unioning this one, the two components by linking parent of x to the parent of y, right? So next, let's move on with this one. So any vertex with degree more than 2 cannot belong to exactly one simple cycle. Cannot belong to exactly one simple cycle. This we had discussed in the approach clearly, right? So then also we have to print no in that case. So let's write one more for loop here. So this one will be same for uh, int I equals 1, I less than or equal to m. So this one will be I plus plus. So this one has to be n, not m. Sorry. Yeah, this is fine. So let's write the simple if condition here. If a of I, if a of I, if it is greater than 2, then let's do one thing. Or let me write this one and the next. This one next line. Yeah. A of I greater than 2. Then I'll just go with the out dot println of no. This is fine. Yeah. Now let me go with the out dot flush actually. Out dot flush. Finally return. Finally return. Right. So this is fine, man. Yeah. Uh let me come out of this one entirely. If we reached here, construction is possible. Yeah, construction is possible. If the construction is possible, then we have to print s, right? Then we have to print s along with the this one. Yeah, then we have to print s along with that. We have to this one. We have to print the number of edges and what edge we have added. That one also we have to print these three things, right? So we have discussed this one. Yeah, now I can just write it in this way. If it is possible, we have to print s, right? So I'll just go with here println along with yes here. This is fine. Let me go with out dot println of n minus m. We have discussed this one, right? So this is fine, man. Let's move on with the further things, man. So now let's go with a greedy addition. Now let's go with a greedy addition. So this one we have discussed. What if a of I is less than 2, right? So we have to print the number of edges as well as the particular edge that we have added to add basically in simple terms. So let's go with a greedy addition. So this one in I equals to 2, I less than or equal to n, I plus plus. And let me go with while loop here. If a of I less than 2, then let me go with int answer equals I plus n not equal to 1, then let's display 1, or let's go with a let's display 0. This is fine. Yeah. Next, what shall we do? Let's try the candidates j from answer to n to find the lexicographically smallest valid. This one. What do we call? Mm, Smallest valid partner, basically in simple terms, right? So this is fine. Yeah, let's do that. So we have to go with one more for loop man here. So this one will be for j equals answer j less than or equal to n. So let me increment j here. So within this for loop, let me do one thing here. Let me go with a simple if condition here. If a of j, if it is less than 2, and also n less than or equal to 2, valid ones, right? We are considering the valid one. Or m plus 1 here, which is equivalent to the value n, or let's go with find of this one. Find of I basically, find of I not equal to find of j, not equal to find of j, then what we will do, we have to print the chosen edge, nothing but the I comma j, right? So the edge to add, the chosen edge to add basically. So how can we write that one? Open dot println I along with that one, we need space between the edges, right? So this one, see here, 1 3, we need space between them, right? 1 and 3. So let's leave the space as well. Along with it, j, I and j are the edges, 1 and 3 in the first example that they have given. So here I have to append. Yeah, this we have done this one correctly. Yep. Now let's update the counters. Nothing but one more edge added. So we have to represent that one, right? So let me increment m here. This is fine. And also a of I, let's increment this as well. And this one, j as well, right? Along with the I. Yep. Now, now what shall we do here? So let's go with a this one. Let's union the components of I and j. So this one again, f of find of this one. This time it's I. This is fine. Oh, this one I forget this one. We have to keep this one within the parenthesis, not the square bracket. So find of basically is equivalent to the find of j. So this is fine. Now let's break the inner loop to reevaluate while a of I less than 2 for the same I. Let me do one thing. Let me give you a break. So this is fine. Finally, we are done with the logic. We are left with only flushing the output, right? So let me come here. So this one, let me consider out dot flush, right? Out dot flush. So this is fine. Yeah. We are done with the coding part. So this is fine. Let's do one thing. Let's do one thing. Before checking the code with the different inputs, before checking the code with the different inputs or the examples, let me copy paste the signature starter template. Just give me a second here. Just do this one. Yeah, let me come to the question. So let me copy this one. The output that we need to get here is yes, 1 followed by 1 3. Let's check the same. We have error, not a statement. Which one? Line number 56. This one is within this one main method. Line number 56. Sorry, not a statement. What is wrong here? F kind of. So this is fine. Mm, we have went with and this is also fine. F of fine. Oh, this one again. This has to be within the parenthesis. I said this one multiple times while writing. This one as well. So this one parenthesis, not the array. Let me run this one again. Again, this one we have now it is correct, right? F of find of x. Oh, this one I have to close it here itself. Let me remove this one over here. Right, so now this has to be correct. Let me run this one. Hmm? Failed. So let me run this one again. So something is wrong here, man. Let's check what is wrong. So what mistake I have done here is, so we are starting from the this one, I equals 1 basically. So here I have given 2. The line number 69 actually. So let me run this one now. This has to work. Yeah, yes, 1, 2, 3. So this creates an indefinite loop actually if we give I equals to 2, right? So this is wrong. So we have to start from I equals 1. So now this is working, man. Yeah. Now let me do one thing. This is the only example, right? So this is fine. Now let me copy. We are getting the correct output here, desired output. So let me copy this one entirely, the code. Let me hit the submit code button. Let me choose here this one E, right? The last one. Paste the code and let me hit the submit button. So this is somewhat this one medium question. So this we can solve. Not easily, but yeah, we can solve this one peacefully. Let's wait for some time. Let's wait for some time. So yeah, you can clearly see here the verdict that we got here as accepted. So whatever the code that we have written works absolutely correct for all the test cases. We have purely went with this one DS human to solve this problem. Yeah, this one disjoint set union. You can clearly see here we have made use of the find here, right? So we have went with the path compression along with this one to find the representative of x here, right, or the parent of the x. This is fine, I believe. Mm, this is easy, somewhat. Yeah, if you know the algo well, actually, we can easily implement. This is fine. We are done with the this one, this particular problem, right? I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.